All right, let's dive straight into this explainer. When we look at railways, we're usually focusing on the massive trains and those heavy steel tracks. But the actual unseen backbone of modern railways, it's telecommunications. Today, we're going to explore the hidden wires and the light beams that literally keep this entire system from just grinding to a halt.
So here's our roadmap for today. We'll start with the railway's telecom backbone, look at the core functions of copper cables, and the constant threat of interference. Then we'll dive into signal loss and bandwidth issues, before wrapping up with the fiber optic future.
Okay, part 1. The railway's telecom backbone. Let's look at the absolutely critical dual-purpose nature of this unseen network. Now here's the thing. While trains physically can roll down a track without signaling, they absolutely cannot operate safely or efficiently without this underlying communications backbone. It's a massive, integrated system. We're talking about carrying voice, everyday operational data, and highly safety-critical control signals all at the exact same time. Just think about the real-world stakes here. You've got a single control center managing incredibly complex, high-speed traffic across a massive geographic area. Every single screen, every device in that room depends entirely on an uninterrupted data flow. If that telecom backbone fails, the operators literally go completely blind. Moving on to Section 2, copper cables and their core functions. Let's look at the traditional workhorse that actually built this network. For decades, this entire system was built on copper. It's historically been the perfect medium for straightforward DC signaling circuits, those classic block bells that signal train movements, and of course, the vital voice circuits so signalers can actually pick up the phone and talk to drivers and track workers. You can actually see this legacy tech out in everyday trackside infrastructure. For instance, a traditional line-side telephone connects via a standard 2-pair tail cable directly right into the main copper route. It's simple, it's robust, and honestly, it's a connection that has reliably worked for generations. But to survive outdoors in some of the harshest environments imaginable, engineers really had to get creative. They use very specific .63 or .9mm gauge copper. The pairs are tightly twisted to cut down on crosstalk. And to survive things like freezing rain, these bundles are heavily protected by moisture barriers and literally packed with petroleum jelly to stop water from getting in and shorting out the whole system. Which brings us to Section 3, the threat of interference. And here is where modern engineering introduces a really severe limitation for those legacy cables. Think about the physical reality out there on the rails for a second. We have thousands of miles of highly sensitive telecommunication cables running right alongside the tracks. But right above them are massive high-voltage electrification systems powering the trains. So what happens when they meet? It's a literal clash between immense power and delicate communication. Well, it builds into a highly critical problem. We're frequently dealing with 25 kilovolt overhead lines. That immense electrical draw of a moving train generates massive alternating magnetic fields. And because those copper telecom cables run parallel to the tracks, this creates electromagnetic interference, or EMI. That magnetic field literally induces stray voltages directly into the communication wires. No way around it.
And the consequences of this EMI are absolutely severe. We aren't just talking about a little bit of static on the line. These induced voltages can easily exceed safe limits, which creates a highly dangerous shock hazard for maintenance staff. Plus, electrical harmonics cause severe noise on speech circuits and can completely corrupt the digital data that is absolutely crucial for safe train control.
All right, Section 4, signal loss and bandwidth. Beyond that external interference, copper also struggles with some major inherent physical limits.
Two major factors show exactly why copper is reaching its absolute limit. First up, high signal attenuation. Over long distances, electrical signals in copper naturally weaken. That means you need constant transmission nodes spaced really closely together just to keep the signal alive. Second, limited bandwidth. Today's railways require huge amounts of diagnostic data and high-def CCTV feeds. Copper wires simply cannot physically carry that massive modern data load. It's like trying to drink from a fire hose with a straw.
This leads us to Section 5, the fiber optic future. To solve these profound electrical problems, the industry had to radically rethink the transmission medium itself.
Fiber optics completely revolutionized the network by just stripping out the metal entirely. Instead of pushing electrical current through copper, fiber relies on pure light. It transmits incredibly fast, short-wavelength light pulses right through a tiny glass core. And because these cables use materials like Kevlar for structural strength, there are virtually no metallic elements inside to catch that nasty interference.
When you compare them side by side, the engineering upgrade is undeniably clear. Fiber optic technology simply bypasses the bottlenecks that cripple legacy networks. Where copper is highly susceptible to EMI, fiber is completely immune. Where copper struggles with bandwidth, fiber easily handles several hundred gigabits per second. And where copper signals fade out quickly, fiber transmits data over massive distances without even needing a boost. The real-world impact of this is just massive. These advantages allow modern railways to implement high-speed, data-heavy digital systems, while entirely ignoring those dangerous magnetic fields from the trains right next to them. Plus, because fiber cables are so much smaller and significantly lighter, engineers can roll them out in much greater lengths. That means far fewer splices along the track, making the whole shebang way more reliable.
Whether it's the legacy copper that got us here, or the cutting-edge fiber optics taking us into the future, the wires and fibers buried along the track really are the absolute lifeblood of the railway. Without them, those massive physical trains are essentially useless.
I'll leave you with this final thought to ponder. Fiber optic technology is vastly superior, for sure. But executing the upgrade from copper across thousands of miles of track, while the system is live and trains are running at full speed every single day, that is a whole new layer of engineering brilliance. Thanks for joining me on this explainer, and I hope this helped illuminate the incredible, unseen backbone of our transport networks.